Hi, in this video, we're going to take a look at feature selection for supervised learning. Okay, so my goal is to build a predictive model using independent variables to predict the dependent variables. Classic machine learning problem. Now, this could be a classification problem. This could be a regression problem. Survival analysis also, anytime that we have a supervised target, that there's a target variable, this will apply. Now, something that we need to consider is what variables am I going to use? Okay, well, if I want to build a good solid model, I don't want to throw every single possible value into it unless I have very little data, because we can have the effect of basically having too many ingredients thrown into the soup. And if I go in my kitchen, I throw in everything I got into my kitchen into my soup, it's probably not going to taste very good. All right, feature selection. What we're going to do, we're going to just basically pick what supports our project and put in only those. One thing that you should always keep in mind is that the more predictor variables I have, the more prone to overfitting I am. So we need to do feature selection. Also, if I'm going to be using dummy variables, I really want to consider binning my categorical variables before I convert over to dummy variables, because the more predictor variables I have, the more prone to overfitting I am. Also, usually we end up actually having a more accurate model. We'll have a model that's easier to maintain in the future if I have fewer predictor variables. I'm going to be, having fewer problems with overfitting. Simpler models with fewer predictor variables are easier to interpret, and also my computation time can be substantially reduced if I use fewer predictor variables. I want to use the best predictor variables, throw out the ones that don't support my project, and and work from there. All right, so why do we do this? Why do I go through and judiciously remove predictive variables I potentially could have used? Well, first and foremost, if I have an irrelevant predictor variable thrown into the model, it can't support what's going on. If it's not related to the target variable, then it really can't enhance my model if I have it in there. Also, if I have, let's say I have two predictor variables that are highly correlated, well, I only need one of them. And having the other one is just basically clogging up the system. And so we'll actually get better accuracy from our models if I only use variables that are relevant. Also, if I have very few predictor variables, or I reduce it down to a very core fundamental list, I'm going to have a lower risk of overfitting. Also, with fewer predictor variables, it's easier to interpret what's going on with my model. It's easier to understand. Also, like feature importance, it will be more clear on what's going on if I have fewer predictor variables in there. Now, one that becomes an issue for me, like on a previous model that I was building where I had quite a large data set, when I tried fitting models with a full range of predictor variables on the initial run, it took so long that I wasn't able to operationally make progress on my project. It would run, eventually I would get it, but it took so long that I wasn't able to do any parameter tuning, wasn't able to dig deeper into the first initial looks of the models. And so what I was doing there, my intention was to use variable importance to decide which variables to include in a simpler model, but it took so long to run. In fact, it took overnight, that what was ultimately happening is that the system would get disconnected because I was using Amazon AWS for this, and I would get disconnected, and all the computation work of the model up to that point was completely lost. And so what I had to do, I had to just go through and judiciously remove things using variable clustering to identify redundant predictor variables and correlation to see which one would be less relevant to our target variable. Also, feature importance can be obscured if I have redundant predictor variables in there. So imagine I have two predictor variables that are perfectly correlated with each other, and I do random forest or stochastic gradient boosting, something like that. Well, half the time this one's getting picked, half the time this one's getting picked, just off of just the random aspects of it. So when I look at feature importance, each of these are going to have half of what I would have if I only include one of them. And so that will make the two predictor variables look less important than they really are. In that situation, I would have been better off with having just the one presentation of the variable instead of both of them. Also, by having fewer predictor variables, we are protecting ourselves from failure of our model when it's in production. All right, so what is going to happen at some point in your career is that you're going to build a model, you're going to put it in production, and there's going to be a variable that is used in there that for some reason the system stops recording it, or maybe the stakeholders decide it's no longer important, or maybe just the business rules change, and you're no longer going to have the variable available to you. And so you're just going to have what I call variable failure. Another situation that will come up if your model is in production long enough is variable drift. This is a situation where the distribution of your predictor variables changes over time. And so imagine I have a batch model that runs every month. Well, every month I'm going to check the distribution of my predictor variables. But if I notice that over time it starts to shift, well, how is that going to impact my predictions? How is that going to impact the prediction and target variable relationship? And so this is something that I'm going to have to deal with. Well, the more variables I have involved, the more alerts I'm going to have, the more I'm going to have to figure this out, the more time and effort I'm going to have to put into monitoring. And so a simpler model is going to be easier for me because it's going to be less work. Also, when I have fewer predictor variables, I expose myself to variable leakage less. Variable leakage is where we use a predictor variable, something that looks like a predictor variable, but it's not, in our model fitting, but at the time of model scoring, it's not available. So imagine that I'm trying to predict whether somebody will pay in collections or not. I'm working on a collections project at work right now, and so my target variable is binary. They paid in collections or they did not. Okay, I've got two possible results. Well, by mistake, I don't understand what's going on with my variables, and I see, you know what? This variable that is amount collected, let's say, looks really good at predicting the likelihood that they're going to pay. Well, that's a variable that is the result of the target variable. And so by accident, unintentionally, I put in a variable that is really the result of the output of the situation, not input. And so that's variable leakage. If I have a lot of predictor variables, I have more exposure to the potential of variable leakage. Now, understanding my variables is how I primarily protect myself from that, by having subject matter knowledge. But sometimes, if you've got a lot of predictor variables that you're working with, you won't know. You might be the first person in your organization that works on a data set, and other people don't know what the fields are, and you'll just be exposing yourself to it by accident. All right, so machine learning algorithms detect patterns in the data like heat-seeking missiles. Let me emphasize that, like heat-seeking missiles. They can easily overfit to noise that's in my training data that's not in the target population. And so I always want to feed quality data. Feature selection is a quality data process. Garbage in, garbage out reminds us that our model is only as good as the data we train it on. And by throwing in junk into the system, I'm going to be degrading my model's performance. All right, so here are some steps in feature selection, and this is just kind of like free form. I spit this out. You talk to other data scientists, they'll disagree on some nuances with this, but this is just kind of similar to what I experience at work. So first and foremost, I'm going to talk to my subject matter experts, my stakeholders, and identify variables that they want to see, like specifically that's important to them, that's important to the project, and variables that they believe are going to be highly useful. Now, part of my process I'm going to work through is I'm going to take those variables, I'm going to look, and I'm going to see, you know what? this one's useful, this one's not. And you're going to end up having like a collection of variables that, you know what, I thought they were going to be really good, but they're not. And I'm going to talk to my stakeholders about it. I might exclude those, I might include those, depending on my project, depending on what they want. Stakeholders might be like really, really adamant that I include certain predictors. In that situation, I'm going to keep it in there because it's part of my project. My goal is to build a model that gets used. And if my stakeholders say this needs to happen, I'm going to do it to get them to work with my model. Also, I'm going to talk to my data engineers. Now, that might be you. You might have to do the data engineering yourself. I'm lucky enough that I have data engineers on my team that do this step for me, but they're going to work through and identify, the database, the schema, the table, and the columns that connect to what we want to have after going through our consultation. If you're in a large organization, there's going to be a whole bunch of databases to work through, and every database is going to have multiple schemas, and every schema is going to have a whole bunch of tables, and tables will have a whole bunch of data fields. And you'll have, what will happen is that you'll have a field of exactly the same name here, field of exactly the same name over here. Conceptually, they are the same, but by the process that this one gets generated, by the process that this one gets generated, they're going to be technically different. So not only do I have to make sure I have relevant data, I have to make sure I'm getting the best source possible. Then I'm going to go through and do my feature engineering to get the best presentation possible. So like, let's say that I have categorical data. I'm going to go through and do my binning to make sure that I don't produce sparse dummy variables, and to make sure that I have the most informative dummy variables I could possibly have. I'm going to apply like Box Cox or Yo Johnson on my numeric variables, but also I'm going to think about doing things like, like for the project I'm working on, I'm dealing with email addresses, and it works out that for a certain number of records, there's no email address. Certain portion of the records do have an email address in the record, and I created a dummy variable of this has an email address or no, it does not, for my feature engineering. Now, after I've done my feature engineering, after I've got a long list of predictor variables, I'm actually going to start like working on the feature selection. So through here, I'm going to have a long list of potential predictor variables, and I'm going to go through and start eliminating ones that look like they're not going to be supporting my project. All right, so I'm going to assess multicollinearity. So I'm going to check to see correlation between my predictor variables. If I'm doing a regression model, strictly regression, or generalized linear models, something like that, I'm going to be leaning on Pearson's correlation for that. But in general, most of the time, if I'm using a more flexible model structure, I'm going to be leaning on Spearman's correlation. Spearman's correlation is rank correlation, and I find it does a better job with things like tree models, for example. Now, if I have categorical data, I can use Kramer's V to make a pseudo correlation between variables, and I'm going to do variable clustering. Now, for variable clustering, I'm going to try and identify like redundant predictor variables, which ones have similar information so that I only need like one of a few in there. And we're going to look at the main effects of each variable. I'm going to train at some initial models and take a look at a variable importance and start trimming things down as I work through. And I want to also evaluate my models to make sure that I have sufficient accuracy. If my model isn't accurate enough, parameter tuning is not the way to go. More than likely, a different model structure isn't the way to go. Maybe feature engineering will improve the situation, but more than likely, if my model isn't accurate enough, I need to get new predictor variables I don't already have. That's usually the best way to go, and that's usually the hardest way to improve a model, is to get some missing predictor variables. And this process is circular, that I complete a step, go back to a previous step, go complete some steps, go back and improve what I did before. And I keep on going back to what I've done before until I get a final result. All right, so let's go ahead and take the house prices data set. Now here, this is not the prepared data that I worked with before. I'm leaving this in like a more of a raw format just so that we can just take a look and see what's going on. I did the data prep, in another video. The reason why I'm doing it this way is because for variable clustering with dummy variables, I would have to like undo the dummy variable aspect and then do Cramer's V. I didn't feel like doing that, so I'm using the raw data on this one. And here I'm just setting up my variables, setting everything up, to be the way I need it to be. Now I'm going to run through correlation analysis, and I prefer to use Spearman's correlation most of the time. I'll use Pearson's if I know that I'm going to do something like logistic regression, multiple linear regression, Poisson regression, generalized linear models, Tweedy, something like that. Otherwise, I like Spearman. You can also use Kendall's tau, very good choice. All right, and so I see that I get a square data frame, a square matrix of the correlations. Minimum correlation is -1, maximum is 1. 0 means, from a statistics point of view, there's no relationship by this measurement between the variables. Now, there's some weirdness things, like if there was like a perfect circle relationship and things like that, that we can get 0 correlation. But typically, when I'm not in a in the more nuanced stuff, when I've got just tons and tons of variables, my interpretation is going to be close to 0 means it's less useful, close to 1 or close to -1 means it's more useful for us. All right, and so now this is a lot. This is a lot to look through, have to wade through, have to figure this out. You know what? I don't know if I can handle all this. So what I'm going to do to make it a little bit easier, I'm going to make a correlation matrix. All right, and so when I see a dark red or a dark blue, that indicates that there's a stronger relationship between the two. Dark red means that for the way that I did this color mapping, by the way, dark red means that there is a positive correlation between the two, and it's very strong. Dark blue means there's a strong negative correlation between the two. And we can go through and look. Now, in this presentation, I have default order on my columns, and it's harder to pick out the details this way. There's a better way to do this. If I use hierarchical clustering, I can change the order of my predictor variables so that they group together, so it's easier to spot trends and groups in what's going on. So here, what I'm going to do, I'm going to go through, I'm going to do hierarchical clustering. Here, I'm using Ward. So Ward works to minimize the variance of a cluster. There's two versions. One is for variance, one is for standard deviation. I can't remember. They minimize similar to each other. In R, it's very clear which one's which. I honestly forgot to look it up before this video, but it's there in the help documentation if you're that interested. They end up being very similar to each other in performance. And so I'm going to go through and plot the dendrogram and show you what it looks like in a moment. Now, hierarchical clustering always uses a distance matrix. So what I'm going to do, correlation is an association measurement. I'm going to take the absolute value of the correlation. You can see the ABS right there. I'm going to do 1 minus the absolute value of the correlation. So correlation is between -1 and 1. Absolute value is between 0 and 1. Close to 1 means strong relationship. Close to 0 means, like weaker linear relationship. And so here, 1 minus is converting it over to a distance. Now, this will not necessarily be actually a distance matrix. If I have any missing values in there, potentially this matrix will not be a distance matrix, but for most purposes, it doesn't really matter. From a theoretical point of view, it could come up, but the type of modeling that I'm doing in this series of videos in this class, it's not an issue, so we don't have to worry about it. All right, and so now I'm going to reorder the columns in a manner to put the variables that are correlated with each other close to each other. So here is the dendrogram showing us the relationship. So when two variables are on a very low fork, when the horizontal part of the fork is very low, that means that they're very similar to each other by this measurement. And so, for example, year built and the year the garage was built are very, very similar to each other. They're not exactly the same, but they're very close. Also, the garage area and the number of cars that go into the garage are very, very similar to each other from a correlation point of view. And then, we can go up and see, the year that was remodeled, and, we can go up here and we can see that if I look at this forking here, this horizontal bar, that corresponds to all of these variables being in one group. In a little bit, we're going to use the dendrogram to decide which variables are very similar to each other. So that means that I could kick one out and I wouldn't really lose a whole heck of a lot. And we'll also find distinct variables for prediction. All right, and so here, now that I've had it sorted, I will zoom out just a little bit. Now you can see that I've got these squares going. Now that I have it sorted, we see basement, like I guess unfinished, basement finished, basement full bath. We can see that these three are very correlated with each other, and they form a subgroup of the variables because of the square. Overall condition looks like it's the next one to come into the group. I also see a square here. All right, and so year remodel add, year built, garage year built, garage cars, garage area. We can see that these are forming a group. We also have another group here. Now remember, I allowed negative correlations in here. This visualization is allowing positive or negative. So dark blue indicates a stronger correlation, just negative. And so we can see that we have a group here also. And so this gives me insight into which variables are highly correlated with each other. And this can help me lead to, like, you know what, I can get rid of this variable because this one over here is going to pick up the slack. All right, now I can also do variable clustering. All right, when I do variable clustering, my experience is that single linkage and Ward are the best two to use. Single linkage is good for finding unique predictor variables. They're unlike any other predictor variables. And Ward is good for finding approximately even groups. And when I say approximately, that's a very, very loose approximately. Now, here are all the different methods supported by SciPy. We got single and Ward. Complete linkage is by far the one that's most accepted by the science community. So you might want to use that just because it's going to be more readily accepted. But we also have average and weighted. Now, centroid and median can give you some weird results on the dendrogram because of how they're computed. So I usually don't rely on them very often, but I'm going to run the code so you can see it. Now, what I do at work is I go through each of these dendrograms and I write down, pencil and paper, which variables look like they're like overlapping and redundant with each other, and I try to identify consistent groups across all of the linkages. And then when I go through and start doing my feature selection, I'll eliminate ones that have other predictor variables in their group. All right, so scroll through. So here's single linkage. Now, why this one is important, notice that up here, I have a group of a single predictor variable off by itself. So how I interpret a dendrogram is that for a group, I go horizontally and slice. All right, so if I go here and I slice in this very narrow range, I'm dividing into two groups. The one that's in this part of the dendrogram and everything else over here. All right, so that means that if I chop into two groups, this variable is off by itself. This tells me that it is unique in its information. If I eliminate that during my feature selection, no other predictor variables are going to pick up the slack. And so I will be hesitant to remove that. Well, like if I have garage cars, I don't need garage area. If I have garage area, I don't need garage cars because they're so correlated with each other. Now, if I go down a little bit more, I can see another one is that a kitchen above ground is another one with unique information. If I remove that, from my model, no other predictor variable is going to pick up its informative value. Now, that informative value may or may not be useful. I don't know. I'm going to keep working through this. I need to go back to like the correlation between this and my target variable. Now, the next one is complete linkage. And so here you can see that it really puts things into 4 different groups. If I was to slice here horizontally, we would have the orange, the green, the red, and the purple groups. And so this gives me an idea of which variables overlap with each other for information. Now I think next one is average. And so average is picking up some smaller groups. This is typically how I like to pick up pairs when I do my pencil and paper writing down aspect. I try to find all my dendrograms, I try to find the pairs that keep on coming up together in small clusters of 2 over and over and over. Now, next one is weighted. And now here I have wards. Now, wards, you can see that put things into 2 distinct groups. And so you can see that the 2 groups have approximately this. If I slice at this point, I have 2 different groups, the orange and the green, and they're approximately equal size. If I wanted to go down to, let's say, 3 groups, then it does a pretty good job of giving me 3 distinct groups if I slice here at the 3. All right, next one is centroid, and you can see the weirdness in the dendrogram. I tend not to use this one as much, but I could use it to just like double check the groups that I have established as I've made it down to this point. And here's median, and the median looks really weird on this. You can see all this weirdness going on. All right, and so now let's go ahead and do the same thing, but now for my categorical data. All right. For categorical, I need to use Cramer's V. Now, the association module in Python will do Cramer's V for me. I don't need to have this custom defined function, but unfortunately, that function at work, I've used that work this past week. The version of pandas that is on the system and the version of association that's on the system like disagree, and so the association function, the Cramer's V function, the association module executes operations that are for a previous version of pandas, and I end up getting a lot of warning and errors. It actually doesn't give me errors. It keeps on running, but it keeps on barking all these warnings at me, and I'm not 100% confident in it, so I'm not using that module here. I built a custom function for this. And so basically my idea of Cramer's V is that I want correlation. It's a measurement of association, but think of it as correlation for categorical predictor variables. Now, the measurement is between 0 and 1. 0 indicates less of a relationship. 1 indicates a strong relationship between them. So this would correspond to what if the contingency table looks like it's independent or homogeneous, my Cramer's V will be close to 0. If it's very far from being independent or very far from homogeneous, then my Cramer's V will be close to 1. All right, and so now I can get what looks like a correlation matrix from Cramer's V, and we can see the values here. And now you'll notice I have a lot of categorical predictor variables. There's no way for me to wade through this, like this. So what I can do, I can once again do variable clustering and plot the correlation matrix. All right, so now with the correlation matrix, I can see like basement, foundation, basement, it, is forming like this square here. And I can see another square here. I can come over central air, paved drive, garage quality, garage condition, garage type, garage finish. These are all forming a square. Like the garage ones are forming a smaller square. And I just keep on going through and looking to see what looks like I've got a strong correlation, very strong Cramer's V between predictor variables. All right, so now I'm going to do a variable clustering just like I did before, but now it's with my categorical predictor variables. And so single linkage indicates that fence is unique. And then street and utilities they're pretty, unique themselves. As I look at that, I want to look at the ones that are off by themselves in the dendrogram. Those are the ones that indicate unique information. And so here, street and utilities are coming down here. And what I typically do at work is I go through and I write down all the pairs that I see. See how I have like pairs for each of these. Here's a pair between these two. And then, I write it down and then I go to the next dendrogram and I look at the pairs and, I write it down for each dendrogram. Then I do, look at the pairs again, keep on doing this over and over and over until I get through all of my, my clustering models. And by the time I'm, through 5 of them, I have a pretty good idea of which variables are collinear with each other. And this gives me a pretty good idea of which ones I keep this one, get rid of this one. I keep this one, I get rid of this one. Now, another way to go through and do my feature selection is to use variable importance from a model. So this could be a regression model. So for multiple linear regression, I could use the t-test statistic on the coefficients. If I'm using ordinary least squares, I could use the magnitude of the coefficients after rescaling also. And that's true for lasso ridge or for linear regression, logistic regression, generalized linear models. Or I can use other ones like tree models where we use, we count the number of times that a variable is used in the splits. And so this can be a very effective way to go through and identify the ones that should be removed first. And so what will end up happening is the ones at the very, very bottom and the ones at the very, very top, you're confident that the result is correct. But in the middle, what's going to end up happening is that you don't know if I have 2 correlated variables in there, that if I removed one, the other one would pop up in the order. And so if I'm going to use this, I want to use this to remove a variable like one at a time. Remove a variable, refit the model. Remove a variable, refit the model, and do this over and over and over. So I want to now, as I go through this process, I do not want to simultaneously remove variables that are correlated with each other. So like garage cars and garage area, I wouldn't want to kick them out at the same time. I would want to remove one of them and leave the other one to pick up to provide the information that it has. And so if I remove both of them at the same time, I'm losing that entire cluster's information. And so remember that if I have redundant that is collinear or correlated predictors, the variable importance is probably going to be lower than it really should be as I go through this process. All right. So here I'm just doing some very, very quick data prep. I'm just scaling everything for this. I ended up using random forest for this. Random forest, any monotonic transformation on your predictor variables will not improve or degrade tree modeling. So I decided to not do anything like Yo Johnson or Boxcox on this one. All right, so if I take the full large data set of predictors, I have 325 predictor variables. All right, well, if I go through and fit this, I'm probably gonna have some junk that I can get rid of. I'm gonna have some, some stuff that's redundant or just not useful. And you'll notice that at the bottom, when I look at the variable importance, you can see the bottom ones up to rounding, they're equal to 0. That means that they were never used in the hundreds of random forests that were hundreds of trees that were built in the random forest. All right, so the feature importance for random forest is that this fraction tells me that about 55% of the splits come from overall quality. 11% is from the ground living area. 5% is from total basement. And I can keep on scrolling down all the way through. And so here I've got a bar plot to show me what is like the importance of each variables. And you can see I just have a whole bunch in here. I have one that's super, super, super important, then a huge drop off. Okay, and so the ones at the bottom probably are not useful. So I want to get rid of them. All right, so another thing I can do, I can use a variable selection function. Typically, most of them are going to go through and do something like forward selection, backwards elimination, or forward back. Forward selection, we start with a variable with no predictor variable. We're using a constant. Then I find the single best variable to put into the model. Then I go and find the second model or second predictor variable to put in to improve the model I already have. Now I have two variables in my model. I find the best variable to add on, I add it on. I've got three. Find the best variable to add on, I add on. I've got four predictor variables. I keep on doing this until I hit a stopping criteria. Backwards elimination goes the other way, that I start with everything in my model. I find the predictor variable that would be the best to remove, and I remove it. Then now I have a new model with one less predictor variables. I find the best variable to remove, I remove it, and then I refit my model. And now I have two less predictor variables than I started out with, and I keep on removing until I hit some stopping criteria. Now, forward back, this is where we do forward selection. Then after every few iterations, I do backwards elimination to double check what's going on. In general, forward selection is going to be the fastest as long as the full model is not the one that we're going to go with. Backwards elimination is usually slower, assuming that there are multiple, significant number of iterations of elimination. If it ends up that nearly the full model is the one to go with, backwards elimination will be faster than forward selection. In general, backwards elimination, in my opinion, does a better job of making sure that everything important is kept in your model, but it takes a long time to run. And we can use recursive feature elimination from scikit-learn to execute a backwards elimination for us. The thing I don't like about this is that the stopping criteria is a predefined number of predictor variables, not model quality. So I don't like this function for this reason. Honestly, I like step AIC from the mass package in R a lot more than this, but I'm really not satisfied with scikit-learn on this front. All right, so here I reduced down my predictor variables. I think I've got, let's see, I got down to 12 off of this. All right, and so now we can see that, like overall quality came up in importance. And as I go through this, the variable importance can only go up for the ones that are left if I'm removing the ones that are very low in importance. And here's that same bar plot, but only on the reduced ones. And so it's much easier to interpret. It's easier to see what's going on. Like really, I might be able to get away with just two predictor variables for this model. But I went ahead and I stopped. Let's see, where I stopped at when it had at least 1%. Honestly, I could have kept on eliminating until I got down to, maybe 5%. That probably would not have hurt the model. All right, now let's go ahead and compare the models. So I'm using my train validation and test partitions, I'm going to evaluate the accuracy of my models. All right, so I've got the full model with all the predictor variables and the reduced. First, let's look at the training set. And you'll notice that they're pretty close. The full model, as expected, has a better training statistic. But it's not a huge difference. When I look at validation, we can see that the full model did better. I actually expected to go the other way. I expected to see that the validation would be worse for full when I ran this. And so we see that validation is better for full than reduced. And you notice I have about an equal difference between train and validation. All right, so this is indicating that okay. So validation is less than training mean squared error. So my loss function here is mean squared error. And so on this, I'm not worried about overfitting because my validation is less than my training. If validation was much bigger than training, I would be worried about this. This is why I love random forest. Random forest tends to work pretty well. And then when I look at my test statistics, about the same, the same conclusion throughout. So with that additional complexity of all over 300 predictor variables, I got this much improvement over that reduced model. This shows that honestly, if I was going to put this into production, the reduced model is the one that I would greatly prefer. Honestly, I would want to keep going and reducing the predictor variables until all of them had at least 5% off of this one. So this one would be gone, and lot frontage would probably go, and probably a year remodel ad would probably be gone also. Don't know for sure, but I would go through one at a time and eliminate predictor variables until I get what I want. All right, so for your homework, what I want you to do, run correlation analysis on your numeric predictor variables, and then train a model and get the variable importance and identify the least important predictor variable, kick it out, and then retrain your model. And you go ahead and do this several times until you feel comfortable with your reduced model, and compare the performance, see how things go. All right, well, that's all I've got for you. Life is short. Do math.